So I used empirical data modeling for my project, and it relies on this idea that in chaotic systems, every variable relies on every other variable. So in a time series, we're going to see all the variables embedded in that single time series. Here we have a time series, and here we have something that is just random. Um, Although in theory, random could be just a very, very chaotic system. Um, so this is all the math that explains how that works, and then this explains how it got this idea of lags, where you take a time series and you offset it by a constant, and it allows, and then you plot that, you plot that into a higher dimensional space, and you get sort of projections of that chaotic space. So you can use that to predict things, which is what I did here. So here we import CUDF. We download some data. So this is their forecasted data, and then this is the actual power usage data from the electricity grid. And I also wanted to have something to predict. So this is the forecast for the next day. This is and the days after that. This is the result for the next day and the days after that. And then this is like all the data from the past few days, so that we have something to analyze. Um, Here we have some data preprocessing, and we load all our data. It runs fairly quickly because my version uses the GPU. This estimates the number of dimensions to have. Basically, how many dimensions should we have that that for every time series you have to lag it by a certain amount, and this estimates how many dimensions we should use. And then this is the meat and potatoes. So um, we have some time series and some data that I want to some variables that I want to change in Plotly. Here we have our simplex projection. So this is one method of using this embedded uh, uh, phase space to predict what's going to happen next. And we have how far in the future we want to try to predict, um, the offset, the number of dimensions, and then here I've noticed that sometimes it doesn't get the y-axis right, so it's sometimes nice to be able to slide that around. We do the same thing for SMAP, which essentially makes a technical analysis of the time series, and uses that to predict what's going to happen next. Um, Here we have a lot of data processing to make sure that it fits into a data frame and it's not too long. And I think I re-implemented some of the features of NumPy. Um, Here we have all the time series that I want to use and the timestamps for those time series, and the labels for those time series. And here I loop through adding everything and converting it to the various data types. And here we have it actually making sure that all the data is the same length, because some of the data is not the same length. And this is all being done for New York City. Um, Here we have Plotly, where we make the graph. This goes through, adds all the figures, so that we can see how everything compares. And then this is all the UI code to show it. So now that and then we have the magic stuff here, that it's just a loop that every second um, it will try to plot with updated variables if anything's changed. And if anything crashes, it will log it, but it will continue execution because we want to avoid crashing for as long as possible. And uh, that we at least avoid having error, an exception end the program. It just crashes the kernel. So let's see what the dash looks like. Well, here we go. We have our power that's coming in for the past few days, and then we have our predicted time series, and we can see that it looks like it sort of gets this area right. Now, one of the things that we can notice is that it's set the dimension to 1, and we're pretty sure that having a higher dimension might give us some accuracy. So let's increase the dimensions a little bit, and then it has to wait 2 seconds because again here I've implemented it as sort of a message queue. It just keeps looping, and because there aren't proper mutexes, or I wasn't able to I didn't really look up mutexes in Python, to be honest. I just used time.sleep. Um, and Here we have the embedded dimension set to 75. I'm not sure if I see much of a difference yet. Sometimes it doesn't refresh. Let's set the number of embedding offset to 2 and see how that changes. Oh yeah, we can definitely see a change there. Um, Now, there aren't great tools for how to set tau. In theory, you should be able to use a lag of 1, but in practice, maybe if you set it too low, you introduce too much noise. Um, Here's the forecast interval. That's how far in the future it's trying to project. And if we turn that lower, I made the UI poorly. If we turn that lower, we can see that it estimates less into the future. So like here, it's just going a little further, but we can also see that maybe it will be a little more accurate because it should be more accurate the fewer the shorter that it has to forecast. Um, Here we have the y-axis where I've shifted it up by 100. So let's see what happens at 0. Oh, and we can see at 0 it actually looks pretty good. Um, and One of the nice things is that uh, I'm running this ideally on a P6000, so it hopefully can have more dimensions. The more dimensions, the better it can represent the information. It doesn't increase in accuracy linearly because if two coordinates are overlapping, um, it has a hard time. Overlapping in phase space, I should say, it has a hard time figuring out what it should do next. Um, so let's try forecasting a little further. And we can see it makes a good effort, and it does get that curve there. Um, but it's not perfect, and part of that is because if we increase the dimensions, let's see what happens. If we increase the dimensions, we can see that it actually gets a little better and a little smoother. Eventually, I run out of GPU memory, which is a limitation of the program. But the nice thing is that because we're using a GPU, we're using dimensions much higher than could be used on the CPU. And we can see that it's starting to get a little more accurate. We can even see that you know the the simplex isn't doing so well. Um, but SMAP is doing a lot better with its sort of the layman's explanation is that it's doing a technical analysis. Where it's sort of going back in time and seeing how each point moved for a given time in phase space. Uh, and then we can see that the the forecast, which you know it um, the forecast that's given is very accurate, but they also had a lot more time data to use than I did. Um, the other project that I worked on um, was I was curious if price actually changed, it actually caused a change in load. So I used something called convergent cross mapping, which takes the idea of that phase space and essentially says that if two time series are part of the same dynamic system, then that um, you should be able to see that one affects the other when it's uh, mapped to the same, or you should see uh, that one time series tends to map to another time series the more points that you check, and they should match in the phase space, if that makes sense. Um, so here we load pricing load and pricing data. We, here it is all loaded in. I grab the names and I have to do a little merge to get the pricing and load data in the same table. I do some pre-processing because convergent cross mapping requires a NumPy array. Here we here we are sort of flattening it into just a two-dimensional array, and then sorry, that happens up to here. So here we have it flattening into a two-dimensional array. Here we have to transpose it, and for some reason we have to transpose it so that for convergent cross mapping to work, so every row is so every array is a row, and the columns are the individual elements. And then it has a dimension estimator that I've used. And we go through, list out all the prices and loads, and here's my password. I'm going to change it. And we have a causal graph and then I wanted to create a causal graph to sort of visualize how price affects load and be able to see interconnections of different sort of different cities and how they affect different prices. And I set a threshold of if it's greater than 0.01%, then I say that it affects another one, it causes the other one, because convergent cross mapping allows us to talk about causality instead of correlation, which is exciting. And then this does some magic to take it from an adjacency matrix, which is what convergent cross mapping outputs as, results as a adjacency matrix, and then it changes it into a list of vertices that are connected by edges here. And so then I plot it, and this is what we get. We have HUD VL price, so we have HUD VL price, and that's connected. We can see that it affects the load for HUD, which we didn't expect, for price, but also affects the genesis price and the central load, and the central price. So there's a complex interaction going on where central load is being affected by HUD load. HUD load's affecting central price. Price is affecting HUD price. I don't know all the different regions in New York, so forgive me for not knowing this. I'm pretty sure this is Long Island. The Long Island price affects a lot of different places. It affects the central load, the GenS price, the HUD price, and the capital price. And the arrows are directional. Are directional indicators of causality. So when the Long Island price changes, it directly affects the capital price. But because the capital price also affects the Long Island price, we can say that they're probably more correlative and have there's some underlying thing driving both of their prices. But we can also see is that it doesn't correlate, it doesn't cause any change in the GNS load. Now the GNS price changes the GNS load. The HUD price changes the central price and the central load. And it affects the HUD load. Now, one thing that this plot here, as it currently shows, doesn't do a good job is showing the weight of the vertice. Oh, here, this is the weight. So we can see that HUD affects the capital load, but only by a factor of 0.2, so 20%. It causes 20% of a change in load. So let's see, like, like if we look at huddle price to load, we can see that it also has a 22% effect. So it's actually it has some effect on the load. So we can see, wait, which one is it? Presumably the one that and we can see that the load has a very small effect on the price. So the price definitely drives it down by a good 20%. Here we can see there's a lot of it affects a lot of different things. So the capital load has a 26%, it causes a 26% change in the HUD load. So the load can be explained by load in other cities also. But it's interesting that the capital load, well, and it makes some sense that the capital load doesn't affect the Long Island load because Long Island load is an island, but the Long Island load affects the capital load, um, and I don't quite understand that. Uh, it does seem low, but it definitely seems to affect the capital load, which I didn't expect that. Um, so I found that sort of fascinating. Uh, you can see some of these are quite low, 14, 15%. And for me, I think, which, it seems kind of low, it seems kind of interesting how low a correlation there is um, between a location's price and the load that is used. Like I would think that it might be much higher because traditional economics says that supply and demand change with price, but it looks like it doesn't have as much effect when we're talking about electricity. So, in conclusion, this is why I think I should get a 3090 GPU. Thank you very much for listening and have a good night.